Welcome intellectuals to our today's wonderful tutorial. So in this video we're going to revise Hooke's law using a question which you can see on the screen. Okay, so I'm going to give a brief review of Hooke's law. So from what we learned, I'm going to write so Hooke's law. So using the question, maybe I read the question first to make it more interesting. So a 0.350 kg object attached to a spring of force constant is free to move on a frictionless horizontal surface. If the object is released from rest at x is equal to 0.100 meters, find the force on it and its acceleration at, you can see this different kind of displacement that have been given. Okay, so whenever I want to understand the force that acts on a spring, this kind of force that acts on a spring is defined by Hooke's law. So what's Hooke's law now states on that force? So it says that the force that acts on a spring, that means which is able to compress or stretch a spring, is direct proportion. So this force is direct proportion to the displacement. Okay, it is direct proportion to the displacement from its equilibrium. So for example, let's have a if this is our if this is our spring. Okay, if this is our spring, you know, two things that can happen to a spring: we can either compress it or stretch it. You know, when we are stretching something, that means we are increasing the displacement. So what is going to happen is that this, before it is either compressed or stretched, this is going to be what we call the equilibrium position. So this is x is equal to 0. So what is going to happen is that once you stretch it, when you stretch it, you apply a force. You are going to say that this is going to be stretched. Okay, let's say maybe you've stretched it to a certain, using an object which has stretched this. So as you can see, there is an increase in displacement. Okay, there's an increase in displacement. This displacement. So when you are stretching something, the displacement is positive. Okay, the displacement is positive. These are some of the things that you should take note of. The displacement becomes positive. Now what I want you to understand is that once you stretch a spring, you are going to see that a spring is going to go back to its original position as long as the elastic limit is not exceeded. So what is going to happen is that there is a force now which is going to take this spring back to its original position, and that force is what we call the restoring force. Restoring force. Okay, the force is what we call a restoring force, and this force is always opposite to the direction. It is opposite to the direction of the displacement. So when we are stretching, the displacement is positive, but the restoring force is going to be negative. As we can see, we stretched it in this direction, but what is going to happen is that we are going to, the force is going to bring this, when you are going to, it's just the same way like the number line is. As we can see, the number line, we have 0, here we have positives, here we have negative. So once we are stretching, we are taking the spring to this side, the displacement is going to be positive, but the force is going to bring this back. So this is the direction of a negative, so the force is going to be negative. That's why this formula is always negative. Okay, it is always negative, just showing that negative doesn't mean that the force is not real. It is real, but it opposes the original motion. Okay, so now let's see what is going to happen once we compress it. Okay, so if this is I'm using the same diagram here. So now let's see, this is our original position. So once we straight it, we push in this direction, we are going to see that this is going to get compressed. Okay, the spring is going to end here, but you can see that the original position is here, that is its equilibrium position. So we're going to see that this displacement, it has been the distance this has been displaced is going to be our what, our displacement when we compress the spring, and this is going to be negative. This is negative displacement. As we can see, we were applying a force which was compressing the spring. But we are going to see that if the spring has not been fully deformed, we talked about the deformation of solids, so the statement is not new for you guys. So if the spring has fully deformed, is not fully deformed, you are going to see that the spring is going to go back to its original position. It's going to go back to its original position, and this force which is taken back to its original position is what we are calling a restoring force. As we can see, x is negative, but this is going to take it to the positive. So when x is negative, the force is going to be positive, the restoring force. So this is the whole information you just need to know. Okay, more advanced questions are going to be solved. So as this is an introduction, and we are going to see a question which is going to make sense of this concept, and this is the question. Okay, so I'm going to read the question again. A 0.35 kg object attached to a spring of force constant 1.3 times 10 to the power 2 newtons per meter is free to move on a frictionless horizontal surface. If the object is released from rest at x is equal to 0.1 meters, find the force on it and its acceleration. So we are asked to find the force and acceleration. Acceleration at different what? At different displacements. Okay, so let's start at so what have we been given? Let's see what we have been given first. Okay, so let's see what we have been given. We have been given the mass to be 0.35 kg. Then we have been given the force constant, that is 1.3 times 10 to the power 2. The force constant, that is the spring constant, 1.3 times 10 to the power 2 newtons per meter. Okay, so we have been asked, the A is to find the force and acceleration at x is equal to 0.1. So at x is equal to 0.1, what is the force? We start by finding the force. So the force is given by x is equal to negative kx. Okay, so we come here by saying we say negative 1.3 times 10 to the power 2 is just 130, just 130. So we say 130, which is negative 130 multiplied by 0.1. So the force is going to be equal to negative 13 newtons. This is the force. Now how about the acceleration? Acceleration, we are going to use that. The formula which we are going to use is this. We say force is equal to mass times acceleration. So we're going to divide by mass over by mass. We cancel. Acceleration is going to be equal to force over mass. This is coming from Newton's second law of motion. So our acceleration will be no other than, so the force is the negative 13 and mass is 0.35. Okay, let me check the mass. Okay, the mass is 0.35. So the acceleration is going to be equal to, so the acceleration is going to be equal to negative 37.14 meters per second square. Okay, so let's go to B. I'm going to explain something at the hands. Let's go to B. So B, we are looking now for the acceleration and force at 0.05 at x is equal to 0.05. So our force is going to be equal to, it's negative k. The spring constant doesn't change, it just shows how the stiffness of the spring, how difficult it is to stretch or compress a spring. That is what this spring constant tells us. So when the spring constant is too big, it is telling us the spring is difficult to be compressed or stretched, and vice versa. So we have 130 multiplied by 0.05. So our force is going to be equal to, so the force is negative 6.50 Newton, and the acceleration is equal to force, which is negative 6.50. Then the mass of the object is still the same. The mass doesn't change. Okay, so our acceleration becomes to be negative 18.57 meters per second square. What do we have next? What about at x is equal to 0? Guys, when x is equal to 0, it means this spring is at its equilibrium position, meaning we haven't yet stretched it or compressed it. That means no force is what is applied. So we are not going to have any displacement, we are not going to have any force and any acceleration. Even before we solve it, we can see that. So we are going to say our force at x is equal to 0. Our force is going to be equal to negative k is 130, but our x is 0. So I have the force, which is 0 Newton. Okay, what about acceleration? Is equal to 0 force over the mass, is 0.35 kg. Acceleration is also 0. Okay, the acceleration is just 0. So let's go now and see the acceleration for the acceleration and force at x is equal to negative 0.05. So I want you to see this and this are one and the same. These numbers are one and the same. The difference is one that the signs are the one that are different. Same applies to 0.1 and this 0.1. The signs are the one that are just different. So it's just a displacement in a negative direction. So what we are going to have is this. Okay. So at x, let me even use white to make it more. This was x is equal to 0.1. So this was x is equal to 0.05. So our d is at x is equal to negative 0.05. So you can see that all the calculations are going to be the same. What are going to change is just the calculator. They are what the signs. So the force is going to be 6.50 Newton, and the acceleration is going to be equal to, instead of negative, we're going to have positive 0.57 meters per second square. Okay, per second square. What else do we have? We have now the last question, which is asking us to find the force and acceleration at x is equal to negative 0.1. This is what I'm saying. Since this is x is equal to the negative 0.1. That means the force is going to be, instead of negative 13, the force is going to be positive 13 Newton. Okay, and our acceleration will be just this, the same, but it's going to be positive. It's going to be 37.14 meters per second square. So, and this is going to make more sense in terms of our definition which we gave, to say that F is direct proportion to the displacement. In this case, just the spring constant, which is showing how stiff the spring is. So I was saying that if the force is positive, x is going to be negative. If x is negative, the force is going to be what? Negative. And this makes a lot of sense. When we had positive x, our force was negative. We have negative x, our force is what? Our force is positive, and the acceleration is also positive. So this is the only thing which you have to put in your mind. Okay, so this is where I hint in this question. So make sure you take the all information which you can see here. So guys, this is the end of our today's tutorial. So now you can see this number. If you need any help, you have any question, queries, you have any question which you need help, you can just WhatsApp me on this number. So as you can see, we've got long videos which we explained all these concepts. So if you want to get access to all our lessons, our tutorial videos, and solved past papers, you can just WhatsApp me on this number so that you can register. We offer tuitions not only in physics, we also have the same physics, biology, chemistry, and math. So you can just WhatsApp me on the same number. Registration is just 70 kwacha per course per month. So you can WhatsApp me now so that you may be part of the team.